Hello, everyone. So today we're going to be continuing our conversation on energy to talk about the first law of thermodynamics, which, because this is not Fight Club, is not don't talk about thermodynamics. But let's go ahead and look at some of the key issues that we might be running into. So as we may have noticed last time, there is a lot of different factors that go into the internal energy of a system. And this means that if I try and determine the absolute energy of a system, it's going to get quite messy quite quick. Because our internal energy, as we illustrated previously, can be thought of as a combination in between our kinetic energy and our potential energy. And we know how to address our kinetic energy, but potential energy gets quite complex because I have things like gravitational potential energy, magnetic potential energy, chemical potential energy, or the electric energy that's caught up in the formation of chemical bonds, and also just the nuclear potential energy that goes into nuclear structure. And it turns out it's going to be very hard to measure some of these terms. For example, even something simple like my gravitational potential energy, am I just talking about the gravitational potential energy with respect to the Earth? Do I need to include the moon? Is it, uh, am I doing this with respect to some given reference point? This actually becomes quite a messy concept when talking about potential energy, because potential energy in and of itself always references how much energy it takes to remove a system from some reference point. And on top of that, most of the time, a lot of our potential energy terms aren't going to be that readily changeable. So if I'm working with a simple chemical system, I'm very unlikely to be moving it up and down a lot. I'm probably not going to be applying that heavy of magnetic fields. And Lord help me if I start transmuting elements to change their nuclear structure. So in this small subset, the only one I often need to worry about is going to be chemical potential energy, or the energy in bonds. And it's still not uncommon for this one to remain fixed as well. So in general, one of the important things to remember about our internal energy is we don't often care what the absolute internal energy is. Instead, what we're really going to care about is how our internal energy is going to change as I apply some force to my system. So in practice, a lot of the times, we're going to focus in much more on the change in internal energy and ignore the actual value itself, because it turns out most of the time it doesn't matter. But if I am going to try and figure out how my internal energy changes, I need to go ahead and think of how this might be something like system specific. So let's go ahead and treat our system as the entire universe. And if I have the entire universe, how can the internal energy change for that system? Well, energy can't come in or go out of the universe because it's everything. So by definition, what we get is a rather important postulate, which is the change in internal energy for the universe is always going to be equal to zero. And this is almost by definition. But it turns out that we can take this relationship and apply it to other systems. Because one of the things that makes the universe kind of unique as a system is that it's isolated. There's no way it communicates with the outside world. And so it turns out that any sort of description chemical or energetic description we can apply to the universe applies to almost any other isolated system. And because this is actually a quite useful postulate, it's given the name of the first law of thermodynamics, which essentially says I can't change the energy of an isolated system. But it has a number of important implications, which is what it's often more known by. So it's often rephrased as the idea that energy can't be created or destroyed, just moved between systems. And this means that there's no such thing as free energy. Energy always has to come somewhere. I can't just spontaneously create energy to run my toaster. And this has become such a contentious issue because everyone loves to try and sell you free stuff, which is never free, that the US Patent Office has actually been forced to file special exceptions to its general patent policies just for perpetual motion machines. So normally you do not actually need to provide a working prototype of a device to the patent office in order to file a patent. It turns out that isn't true for perpetual motion. You can still file a patent, but you're going to need to provide them with a machine and then give them a year to test it and generally expect your patent to be refused. And this actually became quite an issue when in 1979, a man named Joseph Newman went on a big spree trying to sell a new device that created more energy than it consumed, or a perpetual motion machine. And the patent office said, "Well, no, we're actually going to need a working prototype." Newman refused, but he did accept the offer of having a former patent lawyer named Schuler to essentially investigate his device, who said it worked. And this became such a big issue that they had to take the case to Congress itself. At which point, our good friend John Glenn of spacefaring fame pointed out that it turned out that Schuler's law firm actually had represented Joseph Newman's filing for a patent. So, turns out that Congress and the legal system may not have a good knowledge of the laws of thermodynamics, but they sure know a conflict of interest when they see it. So again, this is one of those things that becomes quite a big issue in the public. You'll often hear people saying, "Oh, look at this new perpetual motion machine." And first law of thermodynamics clearly says that the best there's no way to create energy. The best you can hope for is possibly to break even and hope that your machine's an isolated system. As we'll find out later, it's even hard to break even. So most of our focus for the rest of this chapter is going to be focusing in on how internal energy essentially changes over time. So what we're going to be looking at is how energy can enter or exit a system. So we're going to do this by breaking down the movement of energy into two key terms. The first of which is going to be heat. So this is going to be the transfer of thermal kinetic energy. So what you can imagine is I have a hot surface out here, a cold system inside a box. And the gas molecules outside the box hit the wall, and we have essentially that kinetic energy transmitted into the gas molecules inside the box. And that's more or less heat transfer. But we also have a much more usable form of energy called work. So this is going to be the idea of I can also inject energy into the system by, say, taking a piston, pushing it down, and then the actual pressure of the gas inside represents my opposing force. And so the work it takes to push down the piston will end up causing an increase of energy inside the box, usually by heating the system up. And so what we're going to be able to do is, using our first law of thermodynamics and the two possible ways energy can enter our closed system, we can represent any change in internal energy inside the system is going to be dictated by how much heat enters the system and how much work is applied to the system. Now, one of the things I want to point out is going to be the notation we use for heat and work. I do want you to watch out, as this notation can be slightly different from other disciplines or fields, such as physics and chemical engineering. In our notation, a positive value for heat, work, or internal energy indicates that energy is entering the system. And we use this notation because what we really care about is how much energy enters or leaves the system. So we want a positive value to indicate a buildup of energy in the system. Conversely, if energy is leaving the system, this is going to be the same as a negative heat, work, or change in internal energy. And this gives us a fairly consistent format. So whenever you're looking at an energy equation, go ahead and think about, is energy entering or leaving, and then you can assign the appropriate sign. So one of the things that is also worth noting is that we don't always use things like a general change basis because we like to be able to, well, I'm sorry about this, use calculus to describe our systems. We often like describing any change of our system on an infinitesimal basis. So we change our change in internal energy to a du. And similarly, our heat and work become an infinitesimal amount of work and heat, so a dq and a dw value, respectively. So we're going to be using, over the next couple lectures, we're going to be talking about how work and heat can flow in and out of a system. But let's go ahead and start by thinking of this idea of how can I apply work to the system. So one of the simplest ideas is actually one of the oldest ideas that caused the revolution in thermodynamics, which is the advent of steam engines and pistons. Because I can imagine putting my system as a piston where I'm going to compress the system either by applying force from the outside or by simply just putting a weight on the system. So what we're going to be talking about next time is going to be how the energy of a system changes under compression and what implications this might have on the heat, the work, and the actual internal energy of the system. Till then, take care.